Section 3.2. Section 3.2. So last time I left off. What is happening to my camera? Okay, section 3.2 continued. Last time I left off with a discussion about multiplicity, or actually, well, I mentioned that we were going to talk about it. I didn't actually begin discussing it yet. So I'd like to do that now. So let's see. Well, let me remind you what we were doing. So last time we found zeros of polynomial equations. Like, for instance, we might have done something like this. We found the zeros of the polynomial equations, and I'll say usually by factoring. That's pretty much like the method that we have for finding zeros of polynomial equations. So we would factor it, and we would solve it by, once we have it factored, we can split the factors, or rather we can split the equation, set each of these little linear factors equal to 0 independently, which then makes them much easier to solve. And that's what we were doing last time. Last time we found zeros of polynomial equations by factoring, and we noted that they correspond to the, what do they correspond to? The x-intercepts of the polynomial function. So what's going on here? This is a polynomial equation. It's quadratic, in fact. It's a quadratic equation. Polynomials, the more broad definition. A quadratic is a special type of polynomial that's degree 2. And we pulled this from a polynomial function that I would have given you, in the problem, like this, some function that's a polynomial function. And we know that if we want to find the x-intercepts of this polynomial function, which we do want to find the x-intercepts because this whole chapter is about graphing polynomials, then we want to find the x-intercepts, and we know that that is the same as finding the zeros of this equation. So in other words, we set p of x equal to 0 and solve. And then finally, we come down to some solutions to the equation, and these correspond to x-intercepts. So that's what we were doing last time. So if you recall, we were looking at these polynomial functions. We wanted to graph them, right? So we were looking at 2 lectures ago, we were looking at end behavior. The infinity stuff, right? Looking at what happens near or as x tends to infinity and as x tends to negative infinity. And then last class, or maybe it was on, I'm maybe getting my dates mixed up, but it doesn't matter. We've last time we talked about the more local behavior or near the origin, like what's happening on the axes, like where are the x-intercepts and stuff like that. So the overall idea here is that in order to graph polynomial equations, or sorry, polynomial functions, I should say polynomial functions, we want to know end behavior and local behavior. I'll give you a picture of what I'm talking about here. So I'll just pick some generic. Actually, I'll use this one that I wrote back here. So let me write it down again on this page. So just as to have a picture to write down or to draw. This function is a quadratic function. So I kind of already know what the shape of this should be. So there we go. Kind of already know that this should be a parabola, right? But I want to know its end behavior. Let me do this in red and blue. Its end behavior is going to be where it's tending to as x tends to infinity and as x tends to negative infinity. Since its degree is even and it's positive, I know that as x tends to infinity, p of x is tending to infinity. So this is from that page of notes that I gave last time, so I won't go, I won't rewrite them all, but this would be the way to interpret the end behavior. So that tells me, one second, let me see here, make sure I get this, okay. That tells me that my graph is pointing up. Both legs of the graph are pointing up. Okay, and I'm deliberately drawing it like in the appropriate place. I'm trying to do like a color scheme thing here for you. And I also need to know the local behavior, aka the x-intercepts and or y-intercepts. If we wanted to find the y-intercepts, that's usually pretty easy as well. Or not as well, I just mean finding the y-intercept tends to be easier than almost anything else. But specifically the x-intercepts are -3, 0 and -2, 0. See, these are x-intercepts. This is the local behavior, so I know that my graph, not near infinity, right? Now I'm talking about, oh goodness. Let's see if I can make this work. Talking about closer to 0, it's crossing these 2 points, -3, 0, -2, 0. That's where its x-intercepts are. So that's telling me like how it's behaving closer to the origin, not all the way out at infinity, just closer, near the axes and everything. And by the way, as the y-intercept for this, which I'm not really bothering with too much here, remember to find the y-intercept, you just plug in 0 for x, and usually the y-intercept just pops right out. In this case, it would be a 6. So I could graph that up here somewhere, but kind of the point of the past couple lectures has been the end behavior and the x-intercepts. So the behavior near infinity, telling you which way the legs should point, and the local behavior, in other words, the x-intercepts. Okay, so that's kind of a sum up of what we've done so far and the motivation for looking at these graphs from these two different perspectives. But we still need to talk about this multiplicity issue. So what if x-intercepts repeat? So we had an example last time. Where did I put it? Got buried in my discrete math notes. Well, I may just make one up then. Okay. Say I have p of x equals x to the 4th plus 5x cubed plus 6x squared. So you'll notice this is pretty much exactly the same as the example I just wrote here, except the degree has been increased. I've added an extra, or rather multiplied on an extra x squared onto all of the terms. So let's see what happens. Okay. If I wanted to, so what's the goal here? The goal is to sketch a graph. And specifically, we're going to look at what happens with the repeated x-intercept, because one of the x-intercepts will repeat. So first of all, let's look at as x tends to infinity, in this case, p of x. Well, the degree is even, so I know both legs are either pointing up or down. And since it's a positive leading term, in other words, it's just a +1 here, then that means both legs are going to be pointing up. towards positive infinity. As x tends to either direction, p of x is just pointing straight up. Okay, so that part, no problem. Now what about the x-intercepts? Well, set the function equal to 0. This is standard procedure for finding x-intercepts. And usually we're going to factor, like pretty much 9 times out of 10, maybe 8 times out of 10, you're going to end up having to factor this to be able to solve for x. First thing I notice I can do is I can factor off a greatest common factor of x squared. Right, they all have an extra x squared, so I can pull that off, no problem. And then I notice I can actually factor this because it's the one we just did, right? So this can factor very nicely into x plus 3 and x plus 2. This trinomial, and I'm just carrying the x squared down, this trinomial factors into these two parts. And just recall, the way to get this is to think about two numbers that multiply to give 6 that also add to give 5, right? And now I split all of these factors, everything that's being multiplied equal to 0, I set them all equal to 0 individually. We've already seen how these latter two go. These last two here go like this, and I end up with those two x-intercepts at -3, 0 and -2, 0. Okay. Now this one though, what does this one give me? Well, x squared equals 0. I can square root both sides and I just get 0 equals, rather I get x equals 0. So the x-intercept in this case is 0, 0. However, there is a little bit more to say here. There is a little bit more to say. We say that this solution has multiplicity 2. So let me come down here and say has multiplicity 2. And the multiplicity 2 is coming from that exponent here. That exponent up here. Okay. What does this mean for the x-intercept? So this is just the solution to the equation. We say the solution x equals 0 has multiplicity 2, but what does this mean for the x-intercepts? This means that the graph bounces off of that corresponding x-intercept 0, 0 instead of going through the x-axis. Wait, yeah, the x-axis. All right. This is going to be the rule. This is going to be the rule when multiplicity is even. And in this case, multiplicity is even, right? It's a 2. This is the rule for even multiplicity. All right, so let me show you what's going on here. All right. Actually, I'll just graph it in Desmos. That'll be better than watching me graph it. So let me go to Desmos. Share my screen. Okay, we don't want to see that. We want to see Desmos. And I'm going to type in the function, which was x to the 4th plus 5x cubed plus 6x squared. All right, so there is the polynomial graph. Now, first of all, end behavior is checking out with what we said. As x tends to infinity, so the right side of the graph is pointing up. As x tends to negative infinity, so the left side, the graph is pointing up. So that's all good. And let's look at the x-intercepts. We have -3, 0, -2, 0, and 0, 0. So there's all the x-intercepts that we expected. But look at that 0, 0 one, the one that has multiplicity 2. Whoop, didn't mean to zoom in that far. It bounces off of the x-axis instead of passing through the x-axis. It bounces off of the x-axis. This is what happens when you have even multiplicity. Okay. If there was odd multiplicity, then the function would still pass through that point. Not exactly the same as these, it doesn't pass through quite as quickly, but the point is what I need you to know is that if the multiplicity is even like this, then you should expect that the function should bounce off of that point. It should bounce off of that point. Okay. All right, so let's do some more examples, and we'll talk about how, actually, I do want to show you how you would graph this function without just obviously typing it into a graphing calculator. How would you actually graph it? Because how do you know, like, should it bounce from above or bounce from below and all that? So if I just sketch that out. So for what knowledge do you need to bring to this? You need to know the end behavior, and you also need to know where its intercepts are. So I know there's an intercept at -3 and -2 and at 0, 0. So I'll just do this graph in purple here. So there's an x-intercept there, an x-intercept there, and an x-intercept there that has multiplicity 2. So if I know that my graph is pointing up on both sides, I need to make use of that fact to help me know how to graph this. So since I know that there's a normal x-intercept at -3 and -2, that means my graph should come down, pass through that one, turn around, pass back through the -2, then it should come up and do something in between, and then it should not pass through the 0, 0 mark. It's only going to bounce off. And since I've drawn this right and I've passed through this one, and bounced off this one, then my line still ends up going up, which is where it should end up. So all of these pieces are coming together to help you graph the function. So let's do another one. Let's call this officially example 1 now. Now, while I'm coming up with an example, do you guys have any questions so far? You can think of some questions while I'm finding a good example. How about x minus 2 to the 4th times x plus 1 squared. Let's see if we can deal with that. All right, so this is a completely different form here. This is completely factored already for us, as opposed to this form, which is not factored. So what are the pros and cons of these different forms? Good thing about this form, now I'm not saying these are the same. They're not the same. I'm just using them as examples of more standard form here, or I should say like just a typical polynomial form versus a factored form. What's the nice thing about this kind of form? You can immediately see the leading term, so that tells you about end behavior, right? So you immediately know what's going on there. Also, you can kind of quickly find the y-intercept if you needed that, right? What's the nice thing about this form, though? Well, it's already factored, meaning we can really quickly find our x-intercepts. A moment. Did I get a chat message? That is from a different class, isn't it? Okay, all right. So I would argue that this one is better, though, because finding the x-intercepts via factoring tends to be like the most work-intensive part, and that's already done for us here. Okay, so let's look at first let's consider the end behavior. Well, we need the leading term. We need to know its degree and the sign of the leading term. Well, to find that, we take the product of all of the x terms, right? So recall that the way we did this is we expanded out the function, x minus 2 times x minus 2. We expanded out, but we're not going to actually multiply it all out because, I mean, that would take like so long to do this. This would be ridiculous, as many factors as there are. All we do is we consider the product of all of the x terms, which in this case is fairly straightforward because they're all just x's. There's no like coefficient up front other than a 1 here and a 1 here. They're all positive, right? So no funny business happening there. It's literally just going to be x times x times x times x times x times x, which is giving me, so x, how many are there? There are 6, right? So giving me x to the 6th. That leading coefficient is still a 1. We've looked at some before where the leading coefficient was like a 2 in here, so that 2 got multiplied by itself a whole bunch, you know, things like that. But in this case, there's nothing like that happening, so our leading term is just x to the 6th. Its degree is even, and the leading coefficient is positive, so we have this relationship as x tends to infinity, q of x is tending up to infinity. So on the right side, this graph is pointing up. On the left side, so remember these facts are coming from the notes I gave a couple days ago. On the left side, the graph is still pointing up. Okay, that's our end behavior done. So you see when it's written in this form, the end behavior is a little bit more work because you have to go search for that leading term, as opposed to the one I did a minute ago where the leading term was just written right up front. Now, but these graphs are behaving the same, right? The last one tended, both legs were pointing up, just like this one. That's because they both have even degree with a positive leading coefficient. All right, now finding the x-intercepts, I set my function, putting s in parentheses because there might only be one, but we know there's going to be more than one. But let's see. So I set the function equal to 0, and then I solve. All right. Now I've got to realize that this is already factored for me, so I can just go ahead and split these. Graph this in Desmos and have it ready. Sure. X plus 1. All right. Now I finished solving these for x, so I can take the 4th root on both sides here. So I can show you what I'm doing here. I'm going to take the 4th root on both sides of this. taking the fourth root on both sides. But of course, the fourth root of something to the fourth just cancels. So I'm left on the left-hand side with x minus 2, but the fourth root of 0 is just 0. So nothing really happening there. And then, of course, that is giving me x equals 2. X equals 2. All right, a similar thing can happen over here. X plus 1 squared equals 0. I'll take a square root on both sides this time. Not a fourth root, but a square root. And that's giving me x plus 1 equals 0 again, and x equals -1. But I should note this multiplicity thing happening here. This has multiplicity 4. From right here, this 4 is what's telling me that it has multiplicity 4. And then similarly, this has multiplicity 2. So when I write down my x-intercepts, which by the way are 2, 0 and -1, 0, right from this and this, these are my x-intercepts with a y value of 0 because that's what we forced the output to be, right? That's how you find the x-intercepts. You force the output to be 0. That means that the graph should bounce off of 2, 0. And over here, the graph, since both of these have even multiplicities, should also bounce, off of -1, 0. And that's it. Those are the only two x-intercepts. There's only two. All right, so putting all this stuff together, we had the function q of x, just to remind you, was x minus 2 to the 4th power times x plus 1 squared. We've got the legs both pointing up because, well, we figured out it's a degree 6 polynomial and the leading term is positive, so we figured all that out. And let me see, 1, 2. And I also figured out that it has 2 unique x-intercepts, and those x-intercepts are happening at 2, 0 and -1, 0, and the one at 2, 0 has multiplicity 4, so it should bounce off there. So it should be like bouncing off here. And also it bounces off over here. And then, by the way, what was the end behavior? Both legs pointing up. So something like this. So it's going to look like a W, right? It's going to kind of look like a W, like a crazy looking W. It's going to be coming down, bouncing off of this one, coming up. Oh, by the way, where is it going to come up and cross the y-axis? We could find its y-intercept. Maybe we should do that real quick. I'll do it in a different color so we know that this was like an extra thing. Let's find the y-intercept. Okay, how do you find the y-intercept? Set x equal to 0. So the way to write that is q of 0, right? Plugging in 0 is giving me 0 minus 2 to the 4th times 0 plus 1 squared. So literally forcing a 0 in for x. And this is giving me -2 to the 4th times 1 squared. So that's not going to contribute anything. What's -2 to the 4th power? Well, it's -2 times -2 times -2 times -2. So I'm getting 16. So my y-intercept is 0, 16. Okay, so that's not going to be on my graph, right? Because that would be like all the way up here somewhere. So what I'll do to represent that is I'll just kind of make my graph shoot up pretty high, just kind of pretend it goes through 16, right? And then it comes back down and it bounces off of the next x-intercept. So it's like a really wacky looking capital W, right? It has 2 x-intercepts, but it bounces off of both of them because they both had even multiplicity. Now, I'm going to show you the graph now, the actual graph, like from that I'm going to let Desmos do. And you're going to see there is a bit of a difference happening in this x-intercept versus this x-intercept. It still bounces, but it's not going to bounce exactly the same. And that's because while they're both even, this one has a higher even number, right? This one at 2,0 has a higher multiplicity. And what that does to the graph is it means that it's going to hang around this x-intercept for longer. So when I graph it, we should expect this one to bounce off pretty much as I've drawn it, this -1,0. But on this side, I expect it to be a bit more flat. It's going to be like, it's going to hang around this x-intercept for longer. Let's go see if we can see that. Let me graph it and then, yep, there we go. So we see that behavior where it bounces off of the -1,0 and it bounces off of 2,0, but you can see how it stays around the 2,0,1 for a bit longer. It bounces off of that left-hand one pretty fast, but it tends to want to stick around this one. See how flat it gets right there around that point? And that's going to happen when you have higher multiplicity. When the multiplicity is higher, the function wants to stick around to the x-axis for longer. So I could even, oh, actually, before I mess with it, I do want to show you that the y-intercept all the way up here at 0,16. So just so you believe me that it is up there. But I could even make this multiplicity even more higher, like still even, so like 10, and you see how fast this one now bounces off and how long this one sticks around. See how much flatter it is now. So that's going to happen as multiplicity gets higher. But what you need to know is just that if multiplicity is even, then it bounces off of the graph. It bounces off of the graph. If I made these both 2, it would bounce nice and symmetrically. See, like that. That's nice. All right. But there was the actual graph. So let's now look at odd multiplicity. Oop, almost. There we go. All right. What was that? Example 1. So the thing with the looking at multiplicity problems, pretty much most of them are already going to be factored, like I gave q of x already factored here. Because to talk about interesting multiplicity problems, I need things that factor really nicely into, little compact things raised to some exponent. And to ask you to factor something like this, like imagine how ugly this would look expanded out. And then to ask you to get it from that expanded format to this format, that's just not really feasible, right? It would take me a long time, I think, to do it. I mean, and to be honest, I wouldn't do it by hand. I think any sane person would just get a computer to do it, right? So that means that a lot of these problems that I'm giving you at this point now are going to be in this already factored form. But you should not think that they will always be like that, because consider that P of X one I gave at the top of the lecture. You can have things in this form where they do look quite scary, but we found that they do factor very nicely when you realize you can pull those extra x's off, right? Like right here, and then you're back in that familiar territory dealing with this other piece that is just a nice quadratic polynomial. All right. All that to say that I am going to give you another little factored one here. Let's look at a x, I don't know, let's say +4 all cubed. Oh, you know what? No. Because I want to be able to see the x-intercept. and that's going to make that crazy looking. Sorry, let me do a different function. I want to be able to see the y-intercept this time. So let's say, make it a little bit more interesting. Negative x plus 1 all cubed, and then times, to be odd again, no, I want it to be even, so let's say x minus 2 squared. I'm going to go have the graph ready so I can pop over and do that. Okay, first thing, end behavior. First thing is looking at end behavior. That's a problem though, because we don't know the leading term. So again, first we're considering, so consider the end behavior. We need leading term so that we know its degree and the sign of it and all that. So I'll say, expanding this out, I'm getting negative x plus 1 times negative x plus 1. You don't have to do this part if you kind of realize what's going on, and you realize I'm just going to take this thing and multiply it by itself 3 times, and I'm going to take this thing and multiply it by itself 2 times, and then multiply those two pieces together, then that's fine. But the way I'm writing it out, I'm actually expanding it out, and then I like to underline each x term. And then I'm going to take the product of all of these x terms with their coefficients. That means that the negative does come down with this x. So I'm going to have negative x times negative x times negative x. Maybe I should wrap those in parentheses so we know it's still a product there. And then times 2 more of these x's. Okay. I'm getting negative x to the 5th for that one. There are 5 of them, right? And negative, negative, negative makes a negative. So that's my leading term. So this is quite different than the past 2 examples I looked at. This one is going to have a different end behavior. So since it's odd degree, then I know that the legs are pointing in opposite directions. They're either like this, like down then up, or up then down, right? And since the leading coefficient is negative, I know that I'm looking at this case here, where the right side of the graph, the right side, so this side, as x tends to infinity, that's the right side of the graph, r of x is pointing down. And on the left side of the graph, where x is tending towards negative infinity, so the left side of the graph, r of x is tending up towards positive infinity. All right, that's the end behavior. Oops. Okay, now for the x-intercepts. I can't wait until I can get back to normal classes and I can have an entire Blackboard to teach on. All right. Trying to keep all this in sort of on the same page. X-intercepts. So we're setting the whole equation equal to 0. So not the unpacked version, right? When they're packed up neat, nice and neat like this, and you're trying to find x-intercepts, you leave them packed up like this because they are specifically set up to be able to make this next step very nice and easy to solve. At least easy relative to how hard it would be to expand it all out, right? That would be a nightmare. So we're taking advantage of the fact that they're all packed up nice and neat for us. We're going to go ahead and split them, set them each equal to 0. And by them, I mean these two factors. Set each of them equal to 0 independently. I'm going to take a cube root on both sides here. Take a cube root on both sides, giving me negative x plus 1 is equal to 0. Right? Cube root of 0, 0 just absorbs that. And then solving for x here, I'm getting x is equal to 1. Right? Because subtracting the 1 would make it negative, and then I have negative x equals negative 1, so x is equal to 1. And I should say that this has multiplicity 3. Has an odd multiplicity this time. And that 3 is coming from the exponent that was on the outside of this packed up factor here. And then similarly, this one is going to be x minus 2 equals 0, taking a square root on both sides, add that 2 over, and I should say that this has multiplicity 2. Not because of that 2, it's just coincidence, it's the same. The multiplicity is coming from the exponent on the packed up root, okay? So that means for these x-intercepts, 1, 0 will pass, oh, sorry, let me say it like this. At 1, 0, the function will pass through, kind of like a normal x-intercept, will pass through. Whoops. The function will pass through. But I'll say parenthetically, but stick to the x-axis, or stick near the x-axis, that's fine. Longer than usual. So when it's an odd multiplicity, it doesn't bounce off. It still passes through the x-axis, but it just, the higher the odd multiplicity, 3, 5, 7, 9, the higher the multiplicity gets, the longer it's going to want to tend to stay near the x-axis. Now over here, this x-intercept 2, 0 coming from that 2, right? The function will bounce off, just like this is similar to examples we looked at a second ago. The function will bounce off of the x-axis. All right, so let's draw a sketch now. I'll give you a second to write that down if you need to. All right. As an extra thing, let's find that y-intercept real quick. You find, oh, it wasn't cute. R of 0 is equal to, so you go plug 0 in for the x values, and you evaluate. This is going to be, of course, negative 0 is just 0. So 0 plus 1 cubed is just 1 cubed. That's not going to contribute anything. And then I have negative 2 squared. So that's giving me 4. Negative 2 times negative 2 is 4. So I have a y-intercept at 0, 4. So that's nice to know. That's just like an extra thing there. It's an extra nice thing to know. So now for the sketch, I'm going to want a y value at least going up to 4. I'll put 4 tick marks in every direction. And then the function, by the way, is negative x plus 1 all cubed times x minus 2 squared. That's what we're trying to graph. Now, I've already said that its end behavior starts up here somewhere. Up, let's see, where did I say that? Let's see. Here we go. Whoops, sorry. All right, as x tends to infinity, well, that's the right side. I tend to think about drawing these from left to right, so let me look at the left first. As x tends to negative infinity, so it's pointing up on the left side, so I'll just kind of maybe just draw like a left line like that. And then as x tends to infinity, so on the right side, the function is pointing down. Now, it's okay if your lines don't perfectly land on these arrows, right? So don't worry too much about that. Those are just kind of like little helpful markers to remind me that in the end, my function should end up pointing up on this side and down on this side. Now, I also have a y-intercept at 0, 4. I can go ahead and plop that down. That's no problem. And I have an x-intercept at 1, 0, and also at 2, 0. So I'm expecting, what am I expecting? Well, this one at 1, 0, the function should pass through. So it comes down, it passes through the y-intercept, passes through 1, 0, maybe sticking to it a bit longer like this maybe, and then it needs to bounce off of the second one, because recall at 2, 0, it bounces off. So it comes back around, bounces off, and then goes down. Sort of like that. So here is the actual graph. We see it's got the right end behavior. On left, it's pointing up. On right, it's pointing down. Now this seems a little weird, but here's the 1, 0, where you see the green line does pass through the x-axis, but it hangs around for a while. It doesn't just like go straight through. It kind of like moseys about, passes through, moseys about, and then it finally turns, it comes down here, it makes a little bump, and then it turns around and it bounces off of that 2, 0 before tending back to negative infinity on the right over here. So there's still things to say, even though we've discussed a whole lot about polynomial functions, there's still all this stuff happening in between with these bumps. And, you know, you might have a question like, well, how do I know, like, this coordinate point seems important because it's like the lowest or highest point of the bump. So how do I find that? And that's a really good question. And as far as I know, well, we could find it using just algebra methods, I think, but the traditional answer to that would be to use calculus to find that. But that's a tool set we don't have, so we're not worrying about that. We're not really worried about how far these bumps go down, because, you know, when I sketched it coming through here and going, the bump was a lot larger, and then I bounced off a 2, 0 and went down, and that's okay. For our purposes, I'm not interested in you being able to tell me like how far how it's acting in between the x-intercepts. You just need to know if it passes through or bounces off according to the multiplicity. Also, finding that y-intercept can help, but in this case, the y-intercept wasn't was not super helpful. It's all the way up here at 4, 0. All the interesting stuff is kind of happening between 1 and 2 down here on the x-axis. So, yeah, all right. Okay. Now, I don't know if I've given you guys problems to mark for review yet. Let me check in the chat if I have. I'll just go peek through there. Oh, yeah, I did. Except you can ignore you can ignore section 3.3. If you scroll up in the chat, I gave 5 problems, 2 from 3.1, 3 from 3.2. In addition to the WebAssign, right? In addition to the WebAssign, those are 5 problems you could look at for review before the exam. Before I let you go, let me double check that that is what I wanted to assign, because I had them written down somewhere else too. Okay, yeah. Right, so in case you missed it, again, exam 3, which is the one we have on Friday, is not covering section 3.3. It's just 3.1 and 3.2. It'll be a short exam. It's going to be all about graphing the quadratic polynomials from section 3.1 and then expanding to a broader class of polynomial functions in general, and graphing those, finding end behavior, finding x-intercepts, y-intercepts, multiplicity issues, stuff like that. And remember, 3.1, we went on a pretty deep dive into quadratic functions, and we looked at finding that vertex, right? That was a big thing for 3.1, finding the vertex of the function, getting it in standard form. That was no, walk in the park. So definitely make sure that you're feeling good about that. I did a nice long video on 3.1 that if you have not watched yet, then definitely watch that. That 3.1 video that's on Canvas. Wednesday, we will review. I'll expect some questions from you guys. And if you just ask me to work straight through the review problems I gave, then that's fine. Those are legitimate questions. Or you can ask specific questions you have about examples, if you want another example of a certain type or whatever. So Wednesday is going to be dictated by what you guys want. So I'm going to stop recording now, and then you guys are free to go unless you have any questions.